Well, thank you so much, everyone, for joining us today. It's my pleasure to be introducing our second speaker of the series. So this is going to be Antonio Almudévar. He's going to be talking about there was never a bottleneck in concept bottleneck models, which is, as far as I'm aware, a paper which is going to be presented in iClear. It's like, yeah, they say the presentation says iClear. That's good. And yeah, so Antonio is from the University of Zaragoza, and you're a PhD student. So I'm very, very happy that you're here. And please take it away. Thank you.
Okay, thank you for your invitation. So yeah, as he was saying before, I'm gonna be talking today about this work called "There Was Never a Bottleneck in Concept Bottleneck Models," and it will be presented in iClear now in April in Brazil. So all of you who are there and wanna chat a bit, I will be super happy. So first of all, I'm gonna start by introducing this idea of concept bottleneck models. The motivation is like basically most machine learning models operate by learning data representations, which are a compressed version of input data. That they have like less information than the input data and more organized information from the input data, basically. But sometimes these representations are not interpretable, or in general, they are not interpretable, which is not necessarily a problem, but in some applications it can be problematic. Some applications, such as medical domain or finance, we want to interpret what's going on inside the model, and interpreting the representations is a good way of understanding what's going on inside the model. So concept bottleneck models are an approach to address this problem of the lack of interpretability that we have in machine learning models in general. So basically, what they try to do is they try to organize the representation space of the models based on a set of concepts that we as humans understand and that in general we have labels for. Um, for example, in the case of medical image domain, we would like to estimate the arthritis grade. So to try to understand better what the model is doing, we could try the model to organize its internal representations based on if the patient has sclerosis or not, the bone spurs, the narrow joint space. So we would be able to understand the prediction of the model based on a set of concepts that we understand. So just to formalize everything, we have an input X and a task Y, and vanilla models, so normal models, obtain intermediate representation set. So set is able to predict Y. That's the only condition that we impose in these models. Simply, we want to be able to predict Y, so our representation set must contain ideally all the information that is necessary to predict Y. Sometimes side information, which is what we call here concepts, is available. So concept bottleneck models train these representations first to predict Y, same as vanilla models, but they also train these representations so each of the components is able to predict a concept. So each of the subcomponents of the representation set, which is what we call set J, must contain all the information about its corresponding concept. So basically, CBMs are claimed to provide better interpretability. Since set J can predict the concept J, we can understand each of the subset of the representations based on each of the concepts. And also, they allow for interventions. So this idea is that modifying just a element of the representation simulates how it would be to modify a concept in the input space, in the input domain. But there's a problem with concept bottleneck models, which is what we call information leakage, which is that each of the components of the representation contains information that is not related to its corresponding concept. And this has like two main problems for two of the features or advantage of these CBMs is that our presentations are now less interpretable since each of the component contains information different since each of the component of the representation contains information different than the concept, we cannot fully understand each of the components of the representations based only on the concepts. And also the interventions performance is worse since by modifying each of the components of the representation, we are modifying C, but we are like its corresponding concept, but we are also modifying other information that can be in the representation. So why is this information leakage happening? First of all, in CBMs, we train them such as set J must be able to predict its corresponding concept. However, this does not imply that set J can predict only a CJ. So they could be able to predict its corresponding concept, but it could be like they could be able to predict whatever else. They could, for example, contain all the information from the input and still be able to predict CJ. So we propose minimal concept bottleneck models, which build upon the CBMs. So in MCBMs, also the representations are trained to be able to predict their corresponding concept, but we also impose another bottleneck in which we want to predict only the concept. So we are ensuring basically that set J contains information only about its corresponding concept. So just as a summary, vanilla models, they just try to predict the task Y, but they impose no constraints on the internal representations of the model. CBMs, apart from predicting Y, each of the components must serve to predict a concept. And MCBMs, apart from the two previous goals, we also impose a bottleneck in which each of the components of the representation must predict only its corresponding concept. So we are ensuring that they don't contain other information that is not related to the concept. So just as a summary of how the different representations could look like in the different models, first of all, in vanilla models, we have that the presentations will be very entangled. We will have information from many concepts in all the representations. Also, each of the components of the representation can have only a part of the information from each concept. In CBMs, we have that, for example, like set 1 contains all the information about its corresponding concepts, which is why we are using darker blue, but they also contain information about something else. For example, they contain information about what we call here nuisances, which is all this information that is in the input X, but is not in our concept set. So we are ensuring that each of the components is containing all the information about their corresponding concepts, but they can also contain information from other concepts or other information that is in the input that is not in the concept set, which is what we call nuisances. With MCBMs, we are ensuring two things. First of all, we are ensuring, like the same way as CBMs, we are ensuring that all the information from its corresponding concept is also in the corresponding representation, and also that each term of the representation contains information only about its corresponding concept. So that's more or less the idea. We could have like fully disentangled representations. So just to formalize everything a bit, we have that the data generative process, we assume that our inputs to the model X are generated by a set of concepts. In this case, we are considering only two concepts, and nuisances, which, as I said before, is all these things that are in the input but are not in our concept set. And also our goal is to predict Y, which is the task to be solved. That's going to be the goal of our model. So vanilla models, what they try to do in general, they try to make predictions, which is what we call Y hat. And to do that, they are obtaining internal representations, which is what we call set. So basically here our goal is to maximize the mutual information between the representations and the task Y. Since the representations must be used to solve the task Y, then we are maximizing this mutual information. And we can easily prove, you can find it in the paper, that maximizing this mutual information is equivalent to maximizing to a maximum likelihood estimator. Then, as I said before, these representations are in general non-interpretable, so concept bottleneck models try to make these internal representations interpretable. So what they try to do is, apart from predicting Y, we enforce that each of the components is predicting each of the concepts. So basically, we are making these predictions of the concepts, which is what we call C hat. And again, like the same way as in vanilla models, we incorporate a new goal, a new objective, in which we trying to maximize the mutual information between each of the representation terms and their corresponding concepts. So this again is a maximum likelihood estimator. Basically, we try to predict the concept as faithfully as possible. And finally, our proposal is to introduce these minimal concept bottleneck models. And to do that, we introduce another variable in which we are making like predictions of our representations based only on the concepts. So the idea here is that, okay, we are obtaining our representations from the input, and if we make that these representations are as close as possible to another representations that are obtained based only on the concepts, we will ensure that our representations obtained from the input will contain information only about the concepts. So basically here, what we want to do is to minimize the mutual information between the representation and the input given the concept. This means that the representation must remove all the information from the input that is not related to the concept. And this is equivalent to minimizing the scale divergence between the output of the encoder, so set, and a prior that depends only on its corresponding concept. So when this scale divergence is equal to 0, we will have that our representations contain information only about their corresponding concept. So to optimize these MCBMs, we have three terms. The first of them is this maximum likelihood estimator of estimation of the task, which is the same as in every vanilla models. We are just trying to predict y. Then the second term is the same as in CBMs. We are trying to use each of the components of the representations to predict a concept, so their corresponding concept. We have this beta hyperparameter in which we control how important this second term is compared to the first term. And then we introduce this last term in our proposal in MCBMs, which is this scale divergence between the output of the encoder and a prior that depends only on its corresponding concept. We have these hyperparameters, this new hyperparameter gamma, which controls the tightness of the bottleneck. So basically, the higher the gamma, the tighter the bottleneck is. So basically, more information not corresponding to the concepts we are removing when we are increasing gamma. So I'm going to show you the different experiments we made to see how these MCBMs perform. So with these experiments, we want to answer three questions. The first question is if CBMs and MCBMs leak information. So first of all, I'm gonna just as a reminder, we had like the concepts and the nuisances, which was all that information that served to describe the input, but was not in the concept set. And here, to make this analysis, we are going to split this information into two subsets. One of them is NY, which is all that information that is in the input, and it's also helpful to predict the task Y, like the final task. And also N bar Y, which is all that information that is in the input, but is not helpful to solve Y. So what we want to analyze is if each of these terms, the concepts and the two subsets of nuisances, are in the representation. So ideally, we'd like that our representation contain only information about the concept, because this would imply that we have a true bottleneck and each of the components is actually encoding only their corresponding concept. But we will see now that these two subsets of nuisances are also contained in the representations in many of the models that we are going to analyze. So to make this analysis, first we are going to use two toy data sets for, like, maybe many of you are familiar with these. First of all is MPI 3D and Shapes 3D. These data sets are images, and they have descriptors for several factors, and we are choosing one factor as the task to solve, one or two factors as the nuisances that serve to or that are correlated to the output or to the task Y. Another factor, which is the nuisances that are not correlated to the task, and the concepts, which are all the remaining factors. So we filter this data set, so any combination of concepts and Y corresponds to a unique Y. So in this So this is the way in which we are selecting these like we are filtering out the inputs to the model. So we are sure that both the concepts and the ny elements are correlated to y. And also we are using three more real data sets, which are Cipher10, CUV, and animals with attributes. In these data sets, we have like a standard classification task in all the cases. Also, we have some attributes for Cipher10. These attributes are obtained using LLMs. For the two other data sets, they are attributes that are given to us. And we are splitting these attributes into two sets, one of them which are the nuisances, and the other one are the concepts. In this case, we saw that all the attributes are more or less correlated to the output, so we assume that these like these nuisances that are not correlated to the task or to the output are the empty set, because all the attributes are affecting more or less the task to be solved. So as a metric, we are using this thing that we call uncertainty reduction ratio, which intuitively is the percentage of the nuisances that is present in the representation. So ideally, we would like these to be equal to 0, because we would like our representations to be removing all the information which is not related to their corresponding concepts. So first, we analyze how much of this information of the task-related nuisances are present is present in the representations. We first see that CBMs tend to remove more information about the nuisances than vanilla models, but they are not removing all the information. We still have a lot of information from the nuisances that are present in CBMs. We also see that some other proposals from the literature, like CEMs or energy-based CBMs, contain even more information than vanilla models from nuisances. So we don't have a true bottleneck in these alternatives. We even have like a weaker bottleneck than CBMs, for example. We also see that autoregressive and stochastic CBMs. I think Sonia was presenting stochastic CBMs last week. We see that in these cases, like basically these two approaches are based on hard CBMs that they are applying like very strong filter to the representation. So basically, instead of predicting the task Y from the representation, what they are doing is binarizing the representation. So if the representation is greater than 0.5, they are setting it to 1, and if it's lower than 0.5, they are setting it to 0. So it's a very strong bottleneck, and they are predicting the task Y based on that hard-coded representation. But the representation itself is retaining information, because the bottleneck is applied after the representations are obtained. So as we can see, we still have information from the nuisances in the representation from of these systems as well. And finally, we can see that in MCBMs, we are removing more information from the nuisances in all the cases, and especially as we are increasing the value of gamma, we are removing more information from the nuisances, which makes sense. Is the expected behavior, since we are since the bottleneck is tighter. We have like a stronger bottleneck. We are trying to remove more information not corresponding to the concept. So we see that our MCBMs remove more nuisances for all the data sets. Then we also analyze if our presentations contain information about nuisances that are not useful to predict the task. This is an interesting point, because what we see here is that our representation from our models, apart from containing information that is not in the concept set, but is useful to solve the task, they also preserve some information that is not useful to predict the concept and is not useful to predict the task. So basically, all these models are preserving information that is not useful at all. Basically, all this thing comes from this idea that deep learning models in general are are a composition of non-invertible functions, which are the layers, and each of the layers is removing a bit of information. But sometimes since we don't have infinite layers, we are not removing all the information that we would like to remove. So many of the information that is useless is still preserved in the representation. And as we can see here, many of like all these baselines are preserving this information that is not useful for the task or for the concepts. And then we see that MCBMs are perfectly removing all this information, no matter the value of gamma. And this makes sense because it's information that there's no incentives to preserve this information because this information is not useful to predict the task, is not useful to predict the concepts. And we have in MCBMs, we have an extra incentive in which we are trying to remove this information. So we can see that we are basically removing this no matter the value of gamma. Also, we wanted to analyze what was the concept's accuracy. Since we are removing information from the representations, we also ask ourselves, okay, maybe we are removing too much information, and apart from removing information from the nuisances, we are also removing information from the concepts, which could be something bad. We can see here that this is not the case, that in general, for all the data sets that we analyzed, all the like especially for low and medium values of gamma, all the information about the concepts is present in the representation, which is good, which is what we would expect. We can see that when we are increasing the value of gamma too much, maybe we start to remove some information about the concept. So basically, we need to play with this trade-off between removing information from the nuisances, but not removing too much information that maybe we could remove some information about the concepts. And finally, we also wanted to analyze the task accuracy. We first see that for vanilla models, CBMs, CEMs, and energy-based CBMs, more or less the task accuracy is pretty much the same for all the data sets, which in theory is good because we are preserving the task accuracy, but it's not necessarily good because here what we are assuming is that the concept set is not sufficient to perfectly predict Y. So basically, the task cannot be fully described by EC. This is like this typical trade-off that we have sometimes in interpretability domains, that if we want the model to be interpretable, sometimes we need to sacrifice some of the performance of our model. So this, in theory, is good to increase the task accuracy, but in this case, some of interpretability, sometimes a truly interpretable model will necessarily have a worse performance. So we have this case of autoregressive and stochastic CBMs that, as I said before, they build upon these hard concept bottleneck models in which they impose this binary bottleneck after the representation. And we can see that in this case, the task accuracy is decreasing a lot, which makes sense because we have that the concept set is insufficient for most of the cases to predict the task. So in theory, this is the behavior that we could expect. And we also see that we see something similar for the MCBMs, especially as we are increasing the value of gamma and the bottleneck is stronger. We are removing more information from the nuisances, from the representation. So all these nuisances that were useful to predict Y cannot be used right now. So the task accuracy is decreasing, which makes sense. The second question that we wanted to answer in our experiments was if MCBMs improve interpretability or give us a more interpretable representations. So we use 3 metrics to evaluate this interpretability. The first one is CKA, or center kernel alignment, which we were using it to measure the similarity between the representations and the concept labels. We also use this entanglement, which measures if set J contains no information about other concepts different than CJ. This metric has a problem, is that it doesn't perform very well when concepts are correlated, which is the case in most of the real scenarios, that the concepts are correlated. And finally, we are using a third metric, which we could see as a kind of adaptation of this entanglement, which for the case in which the concepts are correlated. And we, like this metric, is measuring if correlation between 2 representations do not exceed that correlation between their corresponding concepts. So we have these plots here that show all the results. Let's go step by step. First of all, we see that CBMs, CEMs and hard, like those alternatives based on hard CBMs are improving the CKA and the OIS, but they are not improving disentanglement in general. So yeah, they are increasing the interpretability of the models in general. Also, energy-based CBMs are not improving interpretability in general either, because they are not improving CKA, they are not improving disentanglement, and they are not improving OIS. And finally, we see that MCBMs are improving the interpretability of the model based on the three metrics that we are using. Also, they improve the higher the value of gamma is, which makes sense. Basically, with higher values of gamma, we are removing more information from the nuisances, so our representations are described based on only the concepts, which makes our representations more interpretable. So this table comes from a comment that a reviewer made to our paper, which was basically like, okay, to tune the value of gamma, this hyperparameter that controls what is the strength of the bottleneck. In real life, you don't have labels for the nuisances by definition, because we define nuisances as those things that affect the input, but we don't have labels for. So how could you tune this value of gamma when you don't have labels for these nuisances? So we found out that all these metrics before are very well correlated to the amount of nuisances that we have in our representations, especially CKA and OIS. They are very highly correlated to the amount of nuisances. So we could use these metrics to tune the hyperparameters gamma. Because to calculate these metrics, we just need the concepts. We don't need the nuisances at all. So we can just use these metrics as proxies um, to tune the value of gamma. And finally, our last question that we want to answer is if MCBMs improve interventions. We are showing these plots that are typically shown in the papers of CBMs, in which we have in the x-axis the amount of concepts that we are intervening on, and in the y-axis the error. Maybe these plots are a bit different than others in the literature, because I remind you that we are not using all the attributes or all the factors that we have labels for as concepts. We are just selecting a subset of all these factors as concepts. So first, we can see that for CBMs, when we are intervening on more concepts, the error even increases. Ideally, what we would expect to see is that the more concepts we intervene on, the lower the error. So that's what we expect, and we can see that when we are intervening on more concepts, the error is increasing for CBMs, particularly for Cypher10 and CUV. We also see that autoregressive and stochastic CBMs are palliating this behavior in general, like they are decreasing with the amount of concepts that we intervene on. And finally, we see that the performance for different values of gamma in our MCBMs is pretty much the same, in the sense that the scopes are parallel, more or less parallel, especially for lower, medium amount of concepts intervened. So the value of gamma apparently doesn't affect a lot the intervention performance. And also we see that for the animal with attribute dataset, all the models are performing pretty much the same. We saw in the table before that all the models were removing a lot of nuisances from in this dataset. So this is maybe why all the baselines are also performing pretty well, because all of them are removing information about the nuisances. And then I want to explain a couple of problems that we have with CBMs, like theoretical problems, and they come from the intervention process in CBMs. So basically, the intervention process in CBMs, we have like three parts. The first one, we obtain the representations through the encoder. Then we modify the components of the representation that corresponds to the concepts that we want to intervene on, and we obtain our prediction based on this modified representation. So there's a problem with CBMs, is that we don't know this distribution P of Z given C. As we can see in this graphical model that I showed before, there is no directed path between C and Z. So there are some solutions proposed to approximate this distribution, but I will show you some of the problems of using these approximations. So the first constraint that is imposed to propose a solution to be able to approximate this distribution is that assuming the concepts are binary, or in the case they are not binary, they are binarized. So if we have, for example, a multi-class concept, we could just do one versus rest classification, which is basically doing a multiple binary classification problem. And then there's a second constraint in which the concept head is defined as the sigmoid of the representation. So then simply the inverse distribution, like P of Z given C, is considered to be the inverse of the sigmoid. And these constraints present two main problems. The first of them is that one versus rest classification is worse than multi-class for different reasons. The first of them is that one versus rest classification tends to overpredict the most frequent classes. So as we can see in these toy examples with spirals, we see that the yellow dots in the one versus rest scenario in many cases are predicted as the red class, while in the multi-class this is not happening so often. Also, there's another problem. This is the highest predicted likelihood of our models. And as we can see that one versus rest classification doesn't have like smooth likelihood transitions. So basically what we would expect is that when you are getting closer to the frontier between one class and another one, for example, the blue and green class, you could expect the likelihood to decrease gradually and then increase again gradually when we are getting further away from the frontier. However, we see that in one versus rest, we don't have this behavior. We have that it goes from 1 to 1. We don't have this smooth behavior. And finally, there's a last problem in which in one versus rest, we could be predicting as positive more than one class, and this is problematic. We could be predicting that the correct class is blue and green at the same time, which is in general false, just by definition of the problem. So this is the first problem that comes from using this one versus rest approach. And there's another problem, which is that by using this sigmoid inverse approximation, we are basically doing a violation of Bayesian principles. So since we don't know the prior of our representation, I show you here a case in which the prior of our representation is simply a bimodal distribution, which is very common case in representation learning. When we have, for example, two classes, it's very common to have two different clusters in our representation space. So the prior is the red distribution. So the probability of Z given the class 1 is this dark green distribution. And if like the approximation that we are using with this inverse of the sigmoid function is the light green distribution. So basically we are using the light green distribution to approximate the dark green distribution, and the same for the blue one. And as you can see, they have nothing to do. They are very different distributions. So this problem of not taking into account the prior distribution of the representation are making us to make like bad approximation of the true distribution of P of Z given C. So as I said, like in CBMs, we don't know this P of Z given C, but in MCBMs, we do know this P of Z given C. So basically here we have a directed path from C to Z via this Z hat, which is this which is this prior distribution of Z. And just by marginalizing over this variable, we could be able to obtain P of Z given C. So we could palliate these two problems that I explained before in the one versus rest classification and the lack of the prior knowledge by using this trick in the MCBMs. So just as a conclusion, CBMs do not enforce a true bottleneck, so they are able to predict C from Z, but this is not enough to impose a true bottleneck. This is a problem for both interpretability and intervention performance. And we propose minimal CBMs, which enforce a true bottleneck. Apart from being able to predict Cj from set j, we also impose that set j must contain information only about Cj. And this improves both interpretability and interventions. So thank you very much for listening. And if you have any questions, I'll be happy to answer them or to try to answer them.
Alrighty, thank you so much, Torio. That was really, really great. Are there any questions? Pietro has a question. Pietro, go for it. Start it.
Oh no, there were already 2-3 questions before me. Like I don't want to overstep.
Look, you can get it started, and then we can.
Okay. Thank you. Thank you for your presentation. And I have. So it looks like by introducing this additional component in the loss, this KL, there are a few benefits. Have you tried to use this KL loss also in other architectures, like take SCBMs, SEM, or energy-based CBMs as they are, but just plug on top of them in the loss this additional KL? Would that be possible? Have you tried it?
Sorry, I'm not sure to understand. Like, if it could be possible to introduce the scale divergence loss in regular CBMs, you mean?
Yeah, or like in other CBMs architectures, like the ones you evaluated, like the baselines you evaluated against, like concept embedding models, stochastic concept bottleneck models. Like, it looks like the loss is very similar to the one of a CBM, but you have this extra term. So I'm wondering whether you could improve also this other architecture, like the intervenability in these other architectures, by introducing this extra term here.
Yeah, that's a good point. For example, for the case of autoregressive and stochastic CBMs, maybe it couldn't make sense because they are based on hard concept bottleneck models, which they are imposing this bottleneck after the representation. So maybe you would be doing the same thing twice. But maybe for energy-based and based CBMs and CEMs, it could be interesting. Right now, I don't remember exactly how these two baselines that we compare with work. But yeah, it could be interesting to analyze this. Yeah, it's something we didn't try, but it could be interesting to try. Yeah, you're right. Yeah, that's a good question. And I don't have. Yeah, maybe we could try to find a way of including them.
Because it looks like a more general solution than just another CBM architecture. It could be something that is like parsley that you can use also in other cases.
Yeah, exactly. Since like all this presentation that I made, at the end of the day, what we are doing is to include like another term in the loss function. So maybe this term in the loss function could be added also to other CBM-based models. Yeah, you're right. Yeah, that's a good idea. Thanks for your question. I don't have the answer if it could improve or not, but it's something to think about. Thank you.
Great. Peter, you say you had 2 more questions, but maybe let's go with Sonali first, and then we can alternate.
My question is somewhat related to Pietro's question. So you've shown this, but could you also use maybe this for concept discovery, in the sense that you have an unsupervised objective and then you combine it with this constraint that leads you to discover maybe new concepts?
Yeah, I don't know very well these approaches of unsupervised discovery of concepts. I don't know if like could you briefly explain me or how
this assumes basically that you have concept annotations, right? But in real life, concepts are kind of these things that I would believe are updated. So maybe you have a concept and then later on you discover that it's related to some other concept, and then you discover new concepts, and you would want to optimize how well you predict all of those concepts then as a result. So you'd have one component of basically concepts that you know that you can treat as like supervised concepts and deal with them in the standard way. And then there would be some unknown kind of representation learning. So could you combine it with like other representation learning objectives so that you can still recover some concepts and then learn in an unsupervised way the other concepts?
I mean, I guess like if these approaches are, as I said, I don't know exactly how they do like this discovery. I just recall this, I think, kind of famous result from disentangled literature in which they prove that unsupervised disentanglement without other biases is impossible in general. So I don't know exactly how these supervised discovery of concepts work, but I guess if there are some solutions that are working well for CBMs in general, we could introduce this extra term for the bottleneck as well. So yeah, in principle, I think it could be possible, but I'm not sure because I'm not familiar with this unsupervised discovery of concepts. But in principle, yeah, it's like this idea, as I was saying before, it's kind of straightforward to implement because at the end of the day, it's including a new loss term, which is also kind of easy to implement as well. So in principle, it could be possible. So what we could ensure is that these new concepts that are discovered, we could ensure that the representations are containing only information about these new concepts that are discovered.
Mm-hmm.
Alrighty. Any more questions? You know, I have my own, but I want to know if anyone else has any other questions before I jump and monopolize this channel. So, any questions? All right, I start. Oh, we have one. No.
No. I was trying to put my hand down because it said that my hand was up.
Oh, perfect. No worries. I'll start the hoarding then. I actually do have a question on the so the results of the unrelated nuances, the table where you had with lots of zeros at the bottom. I don't know if the next that one. Okay, so question here. So this sort of tells me that like the models wouldn't be doing that if they wouldn't have the capacity to do so, right? Like it seems like unregularized models have enough capacity to not to store wherever is useless, and it's just doing it because why not, right? Might as well, like it's effort to remove that information if you have the capacity to do so. Do you think if you would constrain the models more, so you regularize them, something like weight decay or something like that, would you see similar results to the regularization that you introduce? So meaning like how can you separate that what you're observing is because the models are not just over-parameterized versus because the KL term they introduce? Because if you're forced to encode the things in the concepts representations and you have no other alternative because you have no capacity to encode anything else, maybe the models just themselves will end up doing that regardless. And this tells me that they have the capacity and they're doing extra things that they shouldn't be doing. So maybe that's the reason why they're doing things wrong. Like how do you that's another explanation for what we've seen, right? So my question is, how do you disentangle these two explanations? How do you know which one is the correct one?
You mean like one possible explanation is that right now the models have the capacity to preserve this information and they don't have like any regularization to remove this information, right?
So might as well do it, right? Like there's no reason not to do it. Okay. So my question would be, I guess, to make it more actionable, would be if I just very heavily regularize the capacity of my model, say by doing some very heavy weight decay, will I see similar results to applying the KL terms I use?
Yeah, I guess so. I guess so. Maybe like some regularization methods, or for example, another alternative to regularization would be to have deeper models. So deeper models in general, I've seen sometimes they tend to remove more information because they are more non-deterministic functions, so they tend to remove more information. But yeah, I think that using like these regularizations or these having deeper models or any other alternative would tend to remove more information. But the advantage of this scale divergence term is that we are targeting very well the information that we want to remove and the information that we want to preserve. Mm-hmm. And maybe if we were using other regularization methods, we could be removing also some information of the concepts. But yeah, ideally, since we have this incentive to preserve information from the concepts with the loss function of the CBMs, in which we try to predict the concept correctly, maybe using other regularization methods could be effective as well. Yeah, maybe yes. I think so. Yeah, this is actually like a regularization
Yeah,
method.
my hunch would be this tool would be better, but you still see a reduced effect on the other case. But yeah, I agree with you. Like, just given because it's doing exactly the thing that we're looking for, you probably will do better in those metrics that we care about, like these ones. But yeah, I would just curious if you try it out, just doing some crazy regularization and see what happens there.
Yeah. I think they could tend to remove, like, also like in this table, the values, I think they could tend to 0 as well with some other regularization methods. Yeah.
Thank you. Sorry, Pietro.
I guess the issue might be that, like, even in the best case scenario where you apply an L2 regularization or weight decay, and you actually remove only the information that is not in the concept, like just redundant information, you're not enforcing that the remaining information is properly stored in each concept. And while with this regularization, so maybe this table would improve, but I'm not sure about that.
Yeah, I think this will, but if you have a sort of concept alignment loss, you have that extra incentive elsewhere to like localize it somewhat. Yeah, I was just curious. I don't know. I still think this will be better. That would be my hunch. If I have to bet, I would say that. But I still think you'll definitely do reduction in this table. I'm not sure in the other ones. But
yeah. I mean, I think this table is like the easiest one to improve because it's the one that is the information that we have no incentives to preserve.
Yeah.
So yeah, I think many regularization methods could be useful for that. Yeah.
Right. Any other questions from anyone?
Hey, Antonio. Awesome presentation, first of all. I have a related question to the regularization one. So for task accuracy, I understand why the approach may not do as well compared to some of the other ones. But I was interested in your results for concept accuracy. So if what we're doing is regularizing such that the model only focuses on learning the concepts, why was the concept accuracy, like why didn't it improve and maybe go to like close to like 100% if that's all the model has to do, right?
Yeah, I mean, in general, you mean why in our approach, if we are just focusing on preserving information from the concept, why this accuracy doesn't tend to 100? I think that's what I understood. Actually,
yeah.
Like, I think it's pretty hard to improve the concepts accuracy from what we get in CBMs. Like, in general, we are gonna see that there's gonna be some concept information that is gonna be very hard to predict. And with CBMs, we are ensuring that, or what we are trying to do is that all the information from the concepts is in the representations. With our approach, we are not trying to we are not trying to have more information from the concepts in the representation, because we assume that with CBMs is like the perfect, like the standard goal, like is the maximum, because by definition they are trying to maximize the mutual information between the concepts and between CJ and set J in the representation. So we cannot do anything better than this goal. And maybe we can improve the approximations or the lower bounds to optimize this mutual information, but we are not trying to have more information about the concepts in the representation. Because this is like a different problem, and honestly, I don't know how I could improve this. But in our case, this information bottleneck is just trying to remove all the information that is not present in the concepts, but it's not trying to increase the information from the concepts in the representation. I don't know if that answers your question.
Yeah, no, I think that does make sense. It's sort of like you're already doing what's optimal from an information theoretic perspective, and so you can't really do better than that unless you kind of change the approach, maybe.
Yeah, maybe using, for example, another architecture that has other inductive biases. could go from 84.9 to 90, for example. But with these architectures, I think that CBMs are doing the optimal, at least from an information theory point of view.
Got it. Thanks.
Thank you for it.
Sorry, I just want to say we have 3 minutes and we were brutally kicked out of this call, unfortunately, because we already given enough money to the overloads. But David, if you can do it super briefly, if you have a question that is very, very brief, please go ahead. Sorry, you're muted. I can see you're actually muted, but we cannot hear you.
Can you hear me now?
Yes, go for it.
Different microphone. Okay. As far as I understand, the regularization you do doesn't really depend on having a task loss, right? So if you would just try to have a model which trains or like is just trying to predict the concepts without having the task loss, you can also do this regularization, right? So like if you have, for example, a sequential CBM or just independent concept encoder and predictor.
Yeah, I think it could be used for exactly, because the regularization term can quickly come back. It doesn't depend on the task. Yes, you can see this red term doesn't depend on the task. So yeah, basically we could use the same approach for sequential CBMs.
Okay, yeah, I think that's good, because also like while they already like reduce maybe leakage a bit because you don't have the incentive to encode task information directly into concept space. If you train it independent of each other, you still, as you showed here, you still don't have the incentive to only encode the concept information. Okay.
Exactly. Yeah. In this case, for example, like what could happen is the nuisance set, these distinctions that I made in the experiments in which I divided the nuisance set into two subsets. It could be only one subset, because there could be, by definition, like there could be a task. So we will have only this second table in which we have all zeros in the last rows of the table. So yeah, you're right. Maybe with sequential we'll be able even to remove more nuisances information. You're right. Yeah, that's a good point.
Yeah.
Thank you.
Alrighty.
Thank you.
Thank you so much. I'm gonna get caught any second now, but yeah, I just wanted to thank you again, Antonio. This was great, and thank you everyone for coming. And we'll see you guys next week as well. We have another talk, so please come by. And yeah, thank you for joining us.
Thank you.
Yeah, thank you very much.
Bye.